a linear regression is. And so we're going to talk about simple linear regression. We're going to talk about, we may talk about a multiple linear regression and non-linearity. In addition to showing you the principles, we're also going to talk about some caveats. Last week when we were talking, I said that the scientific method emerged from philosophy. And philosophy is concerned with the truth. And philosophy also acknowledges that maybe philosophy itself or the scientific method itself is not the only way to arrive at truth. And so there are caveats, even though these are scientific methods, even though we claim with a high level of certainty that they are that they are accurate. There are arguments to be made, and that's why when I teach, I try to invite the other faculty and I say, hey, what do you think about this? So that's the style of teaching that we're going to take, and you're going to experience that as we move in. Let's jump right into correlation. And so a correlation, if you know nothing about correlations, you probably heard someone say snarkily or in some other way that a correlation is not a causation. We're going to talk about that. One of the ways that correlations are measured is through the Pearson correlation. And what it does is it measures the relationship really between two continuous variables. And if you remember, a continuous variable is a variable in which, and this is a technical definition, is a variable in which the distance between 2 points on that variable scale is infinity. And what do I mean by that? Think about the numbers 1 and 2. You might say 1 an integer, 2 an integer. So there's a jump of 1. But for whatever you're measuring to be a continuous variable, the distance between 1 and 2 can be infinity, because you can have 1.001, 1.002, 1.003, and when you get there, you're going to have 1.0001, 1.0002. So numerically, continuous variable is a variable that can have that characteristic. And the Pearson correlation measures the relationship between two variables that are continuous. Okay. Now, what does this Pearson correlation do? And we're going to give an example shortly. It measures the direction of that relationship. It also measures the strength of that relationship. So let's go back and let's speak on our first person. I remember Debbie Thompson from last week, so maybe we will go with Debbie. Why don't we select someone who is by the name Greg Abiasian and Jamila Bolanli. So let's see, let's go back. So feel free to unmute yourselves. I cannot see you. I just switched between screens. I'm back on this slide. So I was saying that, so get ready to answer the question. I was saying that correlation discusses direction. It also discusses strength. Now, and in statistics, when you measure this relationship, you measure it as the R value, the correlational coefficient, or for your sample, and for your population, you measure it as, I believe this thing is called rho. And if you know the correct one, I don't speak any Greek, you can put it in the chat. Or I don't know, whatever it's called. But the point is this, you're measuring a correlational coefficient when you do a correlation, a Pearson's correlation. Now, Jamila, or I forget the other person's name, are you unmuted? If you're unmuted, signify by saying hello. I'm going to ask a question. Or someone else can volunteer. Any takers?
Hello, sir.
Hi, who's this?
It's Yusuf Igho-Osagie.
Good. So Yusuf, here's a question for you. during hot weather or during, I've given the answer away, but okay, during summer, right? The sale of ice cream goes up, but the number of drowning deaths also goes up. Are those two variables related? Are they correlated?
Drowning deaths.
Yeah.
Like that.
Well, death by drowning is death, right? So drowning, yes. Drowning goes up and ice cream sales go up. Are they correlated?
No, I don't think so.
You don't think so? Okay. Does anyone agree or disagree?
I disagree. They are related.
You did. They are they related or are they correlated? That's a good point. And who's the person who said that? Is that Olanli? The person who said I disagree. Can you give your explanation? What do you disagree? And answer the question: are they correlated or are they related?
They are correlated.
They are correlated, but are they related?
I don't think so. They are not.
Does anyone disagree with that answer? Okay. No.
Sir, please, sorry, sir, please, I missed that.
Okay, so I think I was asking Yusuf that during summer, ice cream sales go up, drowning goes up. And I asked if they were correlated. And someone, I believe that's Bolani, came in and said they are not related. And I said that's a good question or a good answer. Is there a difference between being correlated and being related? And she says they are correlated, but they are not related. And that's a good place to start. So does someone want to give an opinion before we continue? And please, because we have 2 hours, feel free. This is a discussion. You know, everyone here is a professional and an expert. So just jump right in so that there are no long pauses before you speak. So someone tell me, does anyone have a different take or does anyone want to contribute to this?
Okay, so you said ice cream sale goes up and
death by drowning also goes up.
Death by drowning also goes up.
Are they correlated or are they related?
Okay, so it would appear as though they are correlated because they are both moving in the same direction.
Okay, I like that. Good. Thank you.
Yeah, but then we would need to know one, the strength, and that is where maybe a regression will come to see if one is actually causing the other or the relationship is independent.
All right. I like the point that you just made. Who's that? Sorry, I can't see the person talking. What's your name?
It's Jerry. Jerry.
Good. Okay.
This Jerry,
I like the way these conversations are going. So Yusuf said they are not correlated because what does ice cream have to do with death, right? And Jerry said they are correlated because as one climbs up, the other climbs up. And Bolani said they are correlated, but they are not related. And these are very important things when you're thinking about numbers and statistics. Now, I want to make a quick statement, then we move forward. Statistics is a science of numbers, and numbers will behave the same. Numbers don't care whether we're talking about red blood count or whether we are talking about grains of rice. The properties of numbers stay the same. So therefore, you need to be able to interpret your statistics and your numbers in terms of context. And the questions and issues that have been raised by these 3 people are showing the issues that you need to consider as a statistician or as a researcher. So the first question, are they correlated? Yes, Jerry got it right. Because if you perform a statistical test, you're going to see that as one rises, the other rises. So and when the cold weather happens, as one drops, the other also drops. So they are correlated. So the answer is yes. Are they related? And this is the one that may shock you a little. The answer is yes. And I said I gave the answer away earlier. Because why are they related? They are not related because they necessarily cause each other, but they are related because during the summer months it is hot, and the hot weather drives people to one, get ice cream. The hot weather also drives people to go more to the beaches and rivers and water bodies to swim. And the more people that swim, the more people that experience drowning. So are they related? The answer is yes. And this is the point I'm trying to make. If you're a statistician, you're not a numbers cruncher. You need to understand not just the principle. Last week, we were talking about when you're thinking about sampling and all the statistical things that you do when you're doing a study, you also have to have important, solid knowledge about how studies are implemented. And we spent some time discussing that. Today, I want you to know that you need to have subject matter expertise. So now you can see that it's not just about correlation. You also have to think, are these things related? What is happening? Is there a web of causation? And you can see that there's an underlying thing. The summer months are hot. Hot weather drives people to ice cream. Hot weather drives people to swim. Swimming causes drowning. It is because of hot weather that these two things and B are related. Are they correlated? Numerically, the answer is yes. But when you are thinking about causation, and that is where we're going to move into when we talk about linear regressions, we're going to talk about that a little more. Good. So Jerry said it is when we look at the strength that we will determine. So I don't like that answer. It's not correct because the strength may not be the answer to tell you whether those two things are related. But Jerry, let's hold on to that. We'll revisit that and I'll tell you why this answer is also true. So remember when I said that your epidemiology, statistics, and the scientific method emerged from philosophy. There's a thing in philosophy called dialectics, and basically it's the ability for you to accommodate two opposite things as being true. So I just said this is not correct. I don't like it, but as we go forward, we'll talk about why Jerry may be correct. Okay, so let's move on. So now what we just established is that things may be correlated, but they may not be related. Why? Because it's the property of numbers. If two things are going up and they are not related at all, they are not related at all, but because they are going up at the same time, if you run a statistical test, you're going to conclude that they are correlated, but they are really not related at all in terms of the principles, in terms of Bradford-Hill's criteria. And we're going to talk a little about that. Those two things it's a nonsense correlation, quote unquote. And nothing comes to mind right now, but I'm sure you can ask Charles GPT and it will give you ideas of two things that rise at the same time, but are really not correlated. But when you plug them into your software, they appear to be correlated. So that's something to keep in mind. Okay, so look at this. So Jerry brought up something that was on the previous slide. We can have two properties of correlation, the direction. And I think it was Yusuf that said one is going up, the other is going up. I don't remember who, but that is direction. The corollary of that, of course, is that sometimes one can be going up and the other is going down. When one is going up and the other is going down, that is negative correlation. When both of them are going up together, that is positive. Yusuf, Jerry, Bolanle, somebody else, tell me, if both of them are going down together, is that a positive or is that a negative correlation? You can put your answers in the chat, you can shout it out, but we are on a roll now, so quickly.
It's a positive
It is a
correlation.
positive correlation, even though both of them are going down together. So basically,
Going down, yeah.
saying is if they are going in the same direction, you consider it positive. If they are going in opposite directions, you consider it negative. Excellent. Thank you very much, Jerry. I recognize that voice. The other thing is the strength, right? So are they going up together very closely? Are they going up? One is running, the other is jogging, but they are climbing up. That is strength, and you can be strong in a negative, you can be strong in a positive, you can be weak in a negative, you can be weak in a positive. Okay, so we're going to do a few. Do we have any other takers? So thank you to the 3 people. Does anybody else want to join this party? I see Ken Langwani. I see someone called Marufa. I see someone called Egide. I see someone called Sharon Ajudua. I see another person called Stanley Moyo. Feel free to, and Taki Pius, I like that name. Feel free to unmute yourself and answer the next set of questions. Okay, so let's move here. So look at this. Do we have any takers? Look at this on the left. So can you tell me why this is a positive correlation just by looking at this scatter plot? I seem to be forgetting my basic biostats. I struggle to remember that this is called the scatter plot, even though it's right here. Can anyone tell me why this is positive? And can anyone tell me why this is a no correlation? So unmute yourselves, go for it, jump in. Okay, no takers. I counted to 10. So when you look at a scatter plot, you can eyeball this. There's a joke that we used to make when I was in grad school, that there's the eyeball test. Sometimes before you even start doing all these complexities, just take a look. What you would see is that this data appears, I made a mistake. Yep, of course I did. This data appears to be fanning out or moving upward. It appears, right? What that means is that as your GHQ-12 score increases, your workload score also increases. And you can see that with this number, this here. You can see your GHQ-12 score is right here, and this is also close to the end. Whereas here, you have this small one, it's less than 25, and this is also less than, let's imagine this is less than 33 or 33, thereabouts. Whereas you cannot have any clear discernment of the direction that this seems to trend to, right? So this is a weak correlation. You can see that our correlation here is 0.19. And we're going to see a little bit more of that. So even though I'm going to say something here, you may talk to a specialist, and what they would say to you is that I don't see, not a specialist, even you guys, and I don't mean you guys are not specialists, but anyone on average, and they would say, no, I don't see that this is fanning upwards. I don't see anything. And someone, feel free, put it in the chat if you don't see anything in terms of where this data trends. But maybe I'm biased because I've been teaching this for a while. I see it. Let's move to the next slide. You can see this is clearly trending upwards. Now, I'm going to go back here and show you something. You see that this is trending. If we agree this is trending upwards, we know the direction. Let's show you this again, direction and strength. So this fellow, or this one, is trending upward, but it is not tight. And then on this one here, top left, it is trending upward very clearly, and it is tight. So yeah, you can, without having your correlational coefficient score, you are able to say this is a weak correlation because you can see that you can just manageably see that it's trending, but it is the numbers, the data points are not tied together. So you can say, well, there is a correlation, but it is not strong. It is a positive and weak correlation, and you can see that with this number. I'm going to show you what people conventionally agree is weak, strong, moderate, and whatnot. But you can see here, look at the correlation 0.98 here, and the correlation here is 0.19, and it is positive. Both of them are positive. Here on top right, I don't see anything. I say this is not, there's no correlation here. And as you can see, there is no correlation value. This one seems to be trending upward. It is not tight, but it is definitely tighter than what we have right here, right? Or is there any contributions in the chat? Any questions? And on the bottom right, you can see, to my mind, this is trending downwards. It is not as tight as this one. So this is a negative correlation, and it is weaker than this. And you can see this is 0.4, 0.3. Okay, I'm going to ask a question before we move.
Excuse me, sir.
Yes, go on.
Okay, so the bottom right chart you're talking about.
This one, right?
You said, you said it's a negative correlation?
Yes.
Because I would think that because it seems to be trending downward, it's still a positive correlation, but it's still a positive correlation, but yeah.
Yes, I like that point. So let's clarify something. So when we say trending, yes, trending down. So trending downward, what trending downward shows is that, let's start. So remember we said negative correlation means that they are in opposite directions. So let's pick an SBP of 120. Pick any one that is on the line. You see that this is one of them. This is another. This is the highest SBP, but this is a low SBP at week 0. And if you pick a low SBP at week 60, this one, you see this is a high SBP at week 0. So when we say trending downwards, I'm suggesting that the directions are negative. As one goes up, the other is going down. So let me do that again so you see. The data points on 120 at week 60 are low compared to the data points at week 60 versus week 0, which are higher. That is what we mean by it's trending downwards. Is that clear? Or does anyone feel differently or needs further clarification?
Sorry, the week 0 and 60 is confusing because I don't see where it is on the chart.
So week 0 is the one on the horizontal axis. Can you see my cursor, by the way? Can you see my pointer? I'm using a pointer to indicate.
Yes, we can see it.
Okay, good. So the horizontal bar is your week 0, whereas your vertical bar is your week 60. So when you look at the higher levels of data at week 60, it corresponds to a lower level at week 0. When you look at a low value at week 60, it corresponds to a high level. So that means when week 60 goes up, week 0 goes down. That is why it's a negative correlation. And when you eyeball a graph, you can tell whether it's positive or negative. If it's trending upwards from left to right, it is positive. If it's trending downward from left to right, so upward trending, positive. Downward trending, negative. This is different from what we're saying when you look at when both of them go down together. Yes, I wish we had another graph that would show you that both of them are going down together, but it's a positive correlation. Maybe we'll do that. Okay, I'm going to move to the next one. I'm sorry, sometimes. Yeah, go ahead.
Yes, this is Ori. So there's a request in the chat box, but I think you've explained again, but you can check it.
Okay. Okay, good. If I've explained again, I will trust you and I will move on. Okay, so let me wrap up because we are wrapping up correlation. A correlation, a numerical statistical correlation does not necessarily mean that those two things are related. Just because you have a statistically significant correlation does not mean they are related. You have to have that broader knowledge about these things. And we use the example of ice cream sales and drowning deaths. And we said they are related, but do they cause each other? No. And we're moving to that. We're going to discuss that shortly. Okay, so let's do this quick example. Feel free to unmute yourself. We've been hearing from the men. Let's hear from the women, if that's possible. So shout out to Bolanle for blazing the trail for the women. A correlation between the price of a ton of cement is correlated with the cost of building a house. And we see that from our study, it is a negative correlation. And Jerry told us that correlations have direction and they have strength. And so what does a negative 0.75 correlation mean? Can anyone jump on the mic and tell us quickly? Does that mean it's negative? Does that mean it's positive? Does that mean it's strong? Does that mean it's weak? And what does it mean in terms of the variables? Are they going up together? Is one going up or is and the other going down?
It's a strong negative.
All right, I like that. And what's happening with the variables?
So as the price of the cement increases, the cost of the new homes go down or reduce.
Right.
Which is counterintuitive.
It is, right?
We're making stuff up here.
Yeah, in an alternate universe, maybe the price of cement is negatively correlated. So that's why I say we are imagining stuff here. I think I had too good a time putting the slides together. So the negative sign says that. So that's what I believe that is. I remember that voice from last week. Is that Debbie?
Yes.
All right. Okay, good. So, and the 0.7 shows strength. So Jerry said there is direction, and Debbie has told us that that direction is negative, but the strength is it is strong. So in our minds, and Debbie used this word counterintuitive, in our minds we sometimes feel like if it is negative, maybe it's weak, but there are very strong negative people in this world. I'm sure you've all experienced them. So negative correlation has nothing to do with the strength, and that is why I use this example to show you that a negative correlation can still be a very strong correlation. Conventionally, I don't know if Ibrahim is on this call, Dr. Abioye, but I'm sure he will tell you that in his line of work, this convention is not really adhered to. So we say that there's no correlation between 0 and 0.25. So look at this. Remember when we're saying some people could look at this and say, man, I don't see any trend. So, and if you are there, you are in good company because the correlation here is 0.19, whereas we've said there is no correlation between 0 and 0.19. And I was saying that okay, let's move on. And between 0.25 and 0.5 is weak and so on. And you can see this. So Debbie said this is a strong correlation because it's greater than 0.7. However, it's going to be rare for you. I don't know, it's not rare. But in many disciplines, a correlation of 0.4 is a cause for celebration. They're like, oh my God, this is so strong. This is because convention is not truth. Remember what we said, even the scientific methodology is not cast in stone. And I'm going to show you what I'm talking about when we talk about linear regressions. Okay, let's do this quickly. Post your answers in the chat. I'm going to be quiet for 1 minute if I can manage that. I'm usually a talker. and post your answers in the chat. And then somebody else get ready to tell me why the answer is the answer and the other answers are not the answers. How do I get to the chat? Okay, I see someone. Let's have it, let's have it, let's have it. Come on, let's have it. I see 2 A's. I see 3 A's. Okay. Well, this might be a simple one. Everyone's saying A. So if you don't know the answer, just type in A, you'll be in good company. Okay, so I see who is someone. Oh, someone said A and B. Ha 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 ha. Okay, Jerry. So Jerry, you have volunteered yourself by being the person. So tell me about this. Jerry, why is A the correct answer? And why do you think B might also be the correct answer as well?
So yeah, from the previous chart, even though we say yes, 0.4 is tending towards maybe the midpoint of the correlation coefficient, but a weak correlation, maybe slightly weaker, would want to err on the side of caution that that relationship may not be really significant or important. Though you still have to test, but yeah, just being the scapegoat here.
Does anyone want to support Jerry's answer that B may be a good answer?
Yes, I do agree that it may be a good answer.
Yeah.
It's just that there can be other arguments against that point when you consider other things. But if we didn't have A, that would be a good have been an answer.
Right. You have made a very excellent point. Would you tell me your name, please?
Humphrey,
you've made an excellent point. So remember what I said. There are arguments to be made. You can make an argument, right? And we just said in some disciplines, a correlation of 0.4, right, is a cause for celebration. I didn't even remember that 0.4 was going to be used in this poll, you know, and so it's not important. No, it's very important. Oh my God, we're going to publish this and we're going to establish that it is a predictor. It is a risk factor. It's a very useful thing to control for if we're thinking about interventions and so on. So yes, but the point that I think that should be made is that you said if A was not there, B would be the answer. And that is perfect because many times we're not looking for the truth because we agree we don't know the truth. We're looking for the best answer given the information we have right now. Okay, now let's wrap this up. We're 10 minutes ahead. Over time, I want to do this in 30 minutes and then spend the remaining 1.5 hours. But you've probably heard correlation is not causation, but correlation can be causation. Has anyone heard about Bradford Hill's criteria? Philosophers for a long time were concerned about what causes does A cause B? You know, does smoking cause lung cancer? Does how your parents treat you as a child determine your life outcomes? You know, does having malaria 3-4 times a year compared to people who don't have malaria cause a child to become a less productive adult in future or less contributory adult in future versus those who don't have malaria 3-4 times a year? Does it cause? And the answer is yes and no. So nobody has seen the smoke from a cigarette make a cell. No one has seen it under a microscope go into a cell and change it to become cancerous. No one has seen it. What we have are our R-squared values, our effect sizes, and over time, multiple rigorous studies have consistently shown that relationship and the probability that you are likely, which is your effect size, to get cancer if you are a smoker. So answering that question directly, does cigarette smoke, actually, do you see change the cell to become cancerous? No. But because of Bradford-Hill's criteria, we agree that smoking causes cancer because there's temporality, which is smoking occurs first, usually before cancer. There's rigorous, there's consistency, rigorous studies have shown again and again that relationship is there, and the effect size, your hazard ratio is very high. But is correlation causation? The answer is also no. Tying it with the example we gave, drowning deaths, ice cream sales, they are correlated. But is it that, do you think that people who get ice cream during summer are like, okay, I'm going to kill myself by jumping into the river, but here's an ice cream first? Or, or does the ice cream make them jump into the river? The answer is no. So when people say correlation is not causation, wait for it. Let them explain. If they cannot give you these sufficient caveats, then they don't really know what they're talking about. It has just become a cliche that everyone uses. Correlation is not correlation. Oh, thank you very much for telling us that, Thank you. Let's move on. And indeed, let us move on. Does anyone have a question about this? About correlation not being causation, causation not being correlation, or correlation being causation? No questions? Okay, means everyone understands or everyone does not understand. Okay, now let's move to simple linear regression. We are 12 minutes past time. Let's take a pause here. I will take a pause since I've been talking for 41 minutes. Okay, I was looking through the chat, and so Jerry, are the slides moving on your end now? Okay, and I see that Jonke had answered this question, so that's good. Thank you. You had answered the question about people swim more during the hot season and have more drowning risk. You're exactly correct. All right, let's go back and let's jump right into simple linear regression. Okay, so remember we had talked about, for correlation, we had talked about strength and direction, or direction and strength. But the thing that we did not talk about was prediction, and Jerry was getting at it, and maybe that's why I said, I don't really like that answer, because you cannot predict from a correlation. You cannot predict. So remember what we were doing. We're like, oh, if at week 12, this is week 12, you have 150, then you have 150 here. This looks like a correlation is up to 1. And someone might say, well, Ebuwa, are you not predicting? No, I'm not predicting. You know why? Because let's use this one. 100 is here. This is on 100. 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 Which of them are we going to pull it down to? We go across and then you pull down. Which of them are we going to pull down to? You cannot predict the other value from a correlation, because in the real world, you don't really see correlations. This is 0.98, which is really 1. You don't see correlations like this. The correlations are usually like this or like this, which is why I said when people have 0.4 there, they celebrate. So what is that? How can you predict and say, remember that your predictions are on average? You're saying on average, we expect. And in statistics, there's something called exchangeability. And I'm just going to tell you at a high level what exchangeability means. You probably heard people say the average person on the street. They're not talking about the poor person on the street, because people think that that's what it means. What it originally, I mean, now that's what it means, right? Because meaning is as people use things. But what people mean statistically when you say the average man on the street, what they are trying to say is that if you put all of us in a sample from the same population, any randomly selected person can represent the whole group. And this is the scientific basis of sampling. We assume exchangeability. Now, I said we assume. So we assume exchangeability. It is not true that the average person that you pick from the street represents or can represent everybody who's on the street at that time, but it is an assumption. And so what a linear regression does is it takes that assumption to say, okay, on average, the average SBP at week 12, that's a bad example, but we are here now. The average SBP at week 12, what would it translate to? Or the average SBP at week 0, what would it translate to on average? Given that the people or the participants in this sample are representative of the population, but also exchangeable with one another. They are the average person on the street. They are the average person in this population. And that is what a linear regression does. It estimates or it predicts when two variables are related to one another or correlated with one another. It can predict or estimate if you have the value of one, predict or estimate what the value of the other will be. Okay, so we say correlation does not give you the tool to do that estimation. You need a linear regression. And with a linear regression, both variables don't have to be continuous. So remember, we talked about a Pearson correlation, which is a correlation of continuous variables, but with a linear regression, they don't have to be. However, the response variable, which is also called the dependent variable or the outcome variable, has to be continuous. Okay, that is what.
Sorry, sir, please say that again.
Okay, the response variable or the outcome variable, also known as the dependent variable, has to be continuous. That is where you use.
Okay, sir, can I ask one quick question?
Please,
Sorry,
go ahead.
Sir, just over the top of my head. What if we are dealing with variables that are discrete? Maybe they are not continuous. Are you saying that Pearson correlation will not work? And what correlation will we use in that point, and what's regression?
Yes, it's a good question. So, So remember that we said, so these are not set in stone, right? What people do, and I struggled with this during my dissertation. People tend to use a, and now I just have an idea that I should have applied 5 years ago. Okay, what people do is they use a linear regression even to do discrete. Now, let me complicate things even further. Is age a continuous variable or is age a discrete variable? We consider age to be a continuous variable, but remember what we said. So remember what we said, that the points between two of them is infinity. So you can be 11.1 years, 11.2 years, great. But there are other properties of continuous variables, right? And let me see if I remember correctly. A continuous variable can also be negative, right? But age, you cannot be negative 5 years old, or a baby's weight cannot be negative 100 pounds, right? And this is an issue. And so we say, you know what? For the most part, this acts like a continuous variable. And so we're going to treat it as a continuous variable. And you're going to see something in one of the examples. So the short answer is, many times when it's discrete, you treat it as a continuous variable. But now when there is a count variable, you can use a Poisson regression. And that's a little different from your linear regression, because now you're counting, you're trying to predict maybe how many people will show up to a hospital on the day Arsenal plays Manchester United, given that everyone wants to watch that game maybe 10 years ago, not today. And so you use a Poisson regression. But most times people assume, because even the idea of a continuous variable is not exactly set in stone. And now let me tell you the problem I faced in my dissertation. I wanted to predict an FIQR score. It's something for fibromyalgia. And the score I was predicting starts from 0 to 100. But every time I predicted it, it would give me values above 100. That does not make sense. It's not just discrete. What we have is that there is a bound. It can either be 0, 1, 2, 3, 4, all the way to 100, but it cannot be 101. And so this frustrated me a lot because I was treating it with a continuous. I think I even reached out to Dr. Abia. What can I do here? And then I just gave up, and now I'm wondering, if I log transformed, made it a much wider scale, and then did a statistical thing to bring it back into those numbers the way we do with cost data, maybe that would have worked, but I'm 5 years too late. Okay. So maybe that would not have worked, but I hope that answers your question. So sometimes you would use a
Yes, thank you.
Okay, good. Now, so what else can we do? So we can also adjust for confounding. Please give me 1 second. I will be right back. All right, my 1 second is up. Okay, so we're not going to talk about confounding today. We're going to talk about confounding. Maybe we'll talk about confounding. Okay, so I don't know if you guys remember your mathematics or physics, but you probably have seen this thing at some point. Even if you did not have a quote unquote science background in secondary school or high school. But let's talk about this quickly. And this is the point I was making to, I don't know whose question. I don't think that was Jerry, but it might be. Your response variable, your outcome variable, your, what's the other word? Dependent variable is your Y, and your predictor variable, your explanatory variable, your independent variable is your X. Keep that in mind. I'm going to say it one more time. It's your dependent, it's your response, because you're trying to predict the response. If I sleep 8 hours, do I feel less angsty? You're trying to predict the response of being angsty. And your predictor variable is sleep. It is what predicts your response. It's your outcome variable because that's the outcome. Your alternate hypothesis or your research hypothesis is that sleep improves mood. And it is your, what's the other one? Dependent, because this is the mathematical formula. Remember what I said, numbers behave the same. They don't care who you are, what you are measuring, numbers behave the same. And in my mind, that is a criticism of the statistical method because biomarkers are not numbers. Okay, so your outcome, your dependent, your response variable is determined or estimated by your X, your independent, your predictor, or what's the other one? Independent, predictor, or I forget. There's three of them. But I probably said it earlier, so we know that it's true. Now, your y-intercept is your outcome, and this is what I was talking to I think Jerry about just now. Is your outcome when your predictor is 0. So, for example, you want to know if the height of babies, or the length, I think babies are measured by length. The length of a newborn baby is predicted by their weight. And you plot this thing. Because numbers behave the way numbers behave, it will give you a y-intercept. Meaning it's telling you that should your baby have a weight of 0, this will be the length of the baby. But there's no baby in the world that has a weight of 0, even ones that that passed on. Many times your y-intercept is actually negative. So it's like, well, if you have a 0x, your 0 weight, the length of your baby will be minus 32 centimeters. You can be like, how, Sway, how? So and this is why you say it is a method. It's a scientific method to understand. It is not necessarily the truth, the whole truth, and nothing but the truth. And the way it's been explained to me is we're trying to capture that relationship. Yes, it's not, we're not saying that this is how it exactly behaves, but it captures the relationship, and that is why we continue to use statistical regression and whatnot. And history over time bears us out that our predictions, our estimations using scientific methods and regressions actually pans out. So we have a high level of confidence in doing this. So I hope you can see that I'm not just explaining what it is we are doing, but the arguments around it, because you're not going to be number crunchers, and someone's not going to tell you that I found a correlation of 0.75 between shoe size and intelligence, and you are going to jump up and say your shoe size is a predictor of intelligence. I know someone's going to say, well, what about stunting? No, that's not what I'm talking about. I'm talking about, you can argue things anyway. So maybe that's a bad example. Maybe shoe size might be a measure of stunting, and stunting is a predictor of intelligence. But you can see that if you don't have the subject matter expertise, you would run away with numbers just behaving like numbers, as opposed to interpreting statistics based on knowledge, of causation, correlation, and how numbers actually work to suggest, not tell us, but suggest the truth about estimations and relationships. Okay, so I just showed you this. There's no need to talk about this anymore. Spent a long time on it. Okay, let's answer this question. I'm going to be quiet for 1 minute. Put your answers in the chat, and then let's have someone else tell us why the answer is the answer. I'm looking at the chat. I see a C.
Sorry, sir, what's the question?
Oh, it's on the screen. Can you see the screen?
No, I think it's my internet. I can't. Okay, I'm seeing it now. So
Okay, good. All right, I see a C. I see another C. Okay, the C's are having it. Do you see? Do you see that it is C? Okay, keep them coming. Thank you for laughing at that joke. Okay, so Marufat, since you laughed and since you were the first person to laugh, that means you're paying attention and following. Tell us why the answer is C. So let's assume that Marufa is okay. Yeah, there you go.
Yes, sir. I think it is. I think the delivery anemia is sorry. So iron supplement is dependent on. So anemia is dependent on whether iron supplement was used or not.
You know that to be a fact, or is that what they are trying to is that what they're trying to, what's the word, determine?
I think that's what they're trying to determine.
Right. So in this case, you think that they're trying to predict. So Jerry has his hand up. Give me 1 second. You think that they're trying to predict the occurrence of anemia in people who use iron supplements versus not using iron supplements. Is that what you're saying, Marufa?
Yes, sir.
So the outcome variable, the response variable, the dependent variable is anemia. I see Jerry has A and C. So Jerry, tell us, you also raised your hand. What do you think?
No. Sorry, scratch that. It's only C.
Okay.
I didn't see. I was reading one as independent, ion as independent.
Okay,
so
good. Okay, so I feel this is really, really easy. So let's move on because of time. Regression by hand, no, never. I think, no, I'm kidding. Well, no, never, no. Not in these days of AI. You know, this equation is useful for simple examples and to demonstrate the basis of regression. In practice, statistical software is used. So, however, let's say this. If you don't understand this one up here, you're going to fall, it's going to be hard for you to understand, especially when you're doing a logistic regression, or especially when you have more than one variable as your independent variable. So let's go over this quickly. So remember what we did here, y is equals to mx plus c. It's the same thing here. This is your mx and this is your c. And your c is your intercept. Your m is your slope, which we're going to call your coefficient, and your x is your x variable. So you sometimes want to use this to understand, like, wait, what are we talking about? So let's say we are talking about the length of the baby and the weight of the baby. So I'm not going to ask questions, but I'm going to say your beta 0 is your, is your y when your x is 0, which is your intercept. It's just changed around. If you take time to understand this, when people are talking, when you're reading a paper, when people are talking about confounding, when people are saying, so how would you predict? And I think we're going to do that next. You're going to have an easier time. Now, your beta 1 is your slope. It is your effect size. So suppose so what you're saying in this case, because it's a simple linear regression, it is going to be the multiplier. You're going to say, well, this is your constant for your yes, so it is your multiplier, it's your constant. So let's say beta 1 was 4. You're going to say if x was 20 kilograms, and beta 0 was 5. You're going to say that your length of your baby will be 4 times 20 plus 5. Whatever that answer is, I believe it's 85. Keep that in mind. We're going to do some work on that. Okay. Now, remember when I said, let's go back. Remember when I said you cannot predict because, for example, if you look at week 24, there are several points on the 100 line, so you cannot just randomly select one. But we said with a linear regression, you can predict. And the reason is that a linear regression looks through, sorry, if I'm giving you whiplash, a linear regression looks through this entire thing and says, what is the best line to fit? Look at this line here. This line, all the points, all the data points do not fall on this line. This graph really looks like, sorry for the whiplash, this, but a linear regression puts the best possible line. Remember when we talked about exchangeability, when we talked about, exchangeability, it puts the best line and we say on average, this is the relationship on average. Okay. There you go. So look at this. So this is, again, if you assume that this thing is trending upwards from left to right, which is a positive correlation, but because it's not tight, it's a weak correlation, and you can see a correlation of 0.4. We seem to like 0.4 today. But if you put a line here, how do you know the line is not here? And if you're looking at this, this is a correlation. Is there a line here? Is there a line, or is there a line here? We don't know. And so this is what a regression helps us do. This is what that formula that we just saw helps us do. It puts the best line, the line of best fit, the line that best fits your scatter plot. It puts that line, and we can make conclusions, not assumptions, conclusions about the relationship and how to predict one variable from the other, or predict the response variable, if you like it that way, from your predictor variable. Okay, so remember I said we're going to do this. So we already did this, but let's go over it. I will be quiet till the clock turns 107 on my clock. Oh, it's already turned 107 until it turns 108, and then we'll move forward. So take some time, look at this, and if you have questions, ask me. Are there any questions? I think regression by hand is fun. Good for you. Yes. I guess a lot of things are fun for a lot of people that are not fun for others. So yes, I how do they say? I celebrate you if that's a thing you like, you know. Yeah. Okay. Let's see. Any other questions? No questions. I feel like you guys know this stuff already, and so let me know if you already know this stuff, and maybe I would ask to teach more complex things that we can do together. Okay. So how do we determine what the best line of fit is? It's called the least squares. This, in my opinion, you should know this because it might help you think through some things. Yeah. So let's talk about it, right? So remember when we said that the data points fall along, the data points can fall anywhere. This is a simplified version. What happens is that the regression line minimizes the distance. It's the line that minimizes the distance between that line and all the points that fall on each point of your x axis. Is that your x axis or your y axis? So I think it's of your you remember, maybe your y. Remember what we're saying, that if this was 100, all the points that fall, oh, it's your y, all the points that fall. So this point E1 falls here, your point E2 falls here. Imagine that your another point Okay, point E3 falls here, right? The line that minimizes the distance between this point and that line is your regression line, right? And so, and so the distance, when the distance is minimized, the assumption is that these are residuals, and residuals really are they're made of noise, you know, but also we also agree that they are also made of variations, because we accept. Remember when we're talking about exchangeability, we said the average person can be pulled out to represent, but that's not true. That's not totally true, right? There's some variability between me and another individual, and so these residuals take into consideration noise as well as the variability between the different participants in the sample. And let me see what this line, so the line we obtain from the lowest possible value is the best line of fit. So it's the line that minimizes that distance. Okay. If there are any questions, unmute yourself and ask. But you can take some time to read up on residuals, because residuals are not waste. You actually, in some statistical methods, you're actually using your residuals to predict your, not just your variability, but actually your estimate, you know. But let's not go into that. I probably don't understand it as well as some other people do. So I think we've done this already, right? Haven't we? But let's look at this for a quick second, because I see that now we're talking about the residual or the error term. Okay, so let's go over this example together. So we did this earlier. We said if your mean SBP was 150, and then there's a reduction of 2.5 every week, and after week 4, your blood pressure, after 4 weeks, your blood pressure would have reduced by 10. I like that if that's true, that over 4 weeks you can have a reduction of 10, and over 8 weeks maybe a reduction of 20 just by exercising. I would like that. So the question is, my friend who participated in the study had a blood pressure of 145 after 4 weeks. Why? We're imagining that this friend did the exercise exactly, but 145 is different from 140, right? So does anyone know why? I probably said the answer earlier, but why would we see a blood pressure of 145 instead of 140 if this friend did the exercise exactly as prescribed? Jumoke, what do you think? Does anyone want to give this a go?
I think probably if there are some co-founders, for example, if the friend probably smokes, so that might actually affect the blood pressure from coming down.
I like that. But will not accept it. Gideon, I see that you said also confounders. Even though you said co-founders, I like that. I prefer co-founders to confounders because they're both contributing together to the outcome. So that's a good one. But we're not going to accept that today. Let's imagine that these people are they're no confounders, right? There's nothing confounding this. The point of this question here is to make the point we were making here, that there is variability from individual to individual. When we say that your exercise would reduce by 2.5 millimeters of mercury, it is on average. This is the expectation. This is our best guess estimate, that the average patient will have a reduction of 2.5 every week. This is not the truth for everybody in the sample. If we average out everybody's change, in fact, if you measure this by individuals, you will find that some people actually have an increase in weight at the end of 4 weeks. Some people have a decrease. Some people have a decrease of 10. Some people have a decrease of 20, maybe 5. Some people have an increase of 10. But when you average out after controlling for confounding, right? Confounding is a good answer, but we will not accept it for this class because we're saying after controlling for confounding, they did the exercise the same way. It is because the idea of exchangeability is not true. There are variations between that average person and other members of the sample. Can you imagine if we were really all exchangeable? Then we would all be the same person. If you could swap me for Yusuf, you know, same clothes, same look, same, then what's the difference? There's no difference. Because people are different, there's a variability. And what we are doing when we're using linear regressions is we are determining what the average expectation is. So the average expectation is that you would have a reduction of 2.5 millimeters of mercury every week on average, but individual variations will be observed. And that is why my friend, and it's not because he's my friend that I'm making the case for him, that is why my friend had a reduction of less than 10 and his blood pressure was 145. Do we understand? Do we understand this point, or do we is this a little shaky? So Jumoke says that 145 is still close, so it still works. I guess that's good. That's another discussion to be had, but I like the way you're thinking about it. The points to note is that because individuals in the sample or in the population, because exchangeability is not true, it's not 100% true. People vary, and because people vary, people have different results. But we can assume on average, that there would be a reduction of 2.5 per week. Okay, and I think this is a cheeky question because after 60 weeks, it will be what? 2.5 times 60 is 150. That means the person would have a blood pressure of 0. So that's it. This one's just a cheeky question. And this is the point I was telling you, that numbers behave like numbers. Numbers don't care that this is a blood pressure measurement, right? So even if you exercise for 60 weeks and this linear regression is telling you that you can have a reduction of 2.5 every week, does this mean that by 60 weeks your blood pressure will be 0? No, the only people with blood pressure of 0 would be dead people. Maybe you'd have exercised yourself to death. I don't know. But you see that numbers are numbers, and linear regressions, what they do, or regressions, or even the scientific method as a whole, what they do is they do the best they can at telling you relationships. They are not the truth. And that is why you should not go into the world and think that what you have determined is better than what, for example, a qualitative researcher determines by interviewing a sample of 12 people. Yeah, maybe you may be more objective, but maybe you also do not know the truth, and maybe they know the truth. Okay, we talked about hypothesis testing last week, so maybe we would not go in depth. If you remember, we said you start with a null hypothesis, and the null hypothesis says there is no relationship. But when you're talking statistically, what does that mean? It means that your beta 1, and let's go back. Remember when I said this is useful for you to understand? Oh, where's that thing? Okay. It says that your beta 1, your multiplier, your slope is 0. This is your null. So we talked about the principle of explaining a null and an alternative hypothesis, and now I'm showing you how it is written statistically. Can anybody tell me, and please be very fast to unmute yourself, otherwise I'll just keep talking, why your null hypothesis says that your beta 1 is 0? Remember that your null hypothesis says there is no relationship, and the clue is going to be found here. Look at this and tell me the answer. My money is on Jumoke to tell us the answer. Okay, Jerry, let's go. Let's go. I would have just lost 50 naira now if but Jerry, let's go. You came off mute. It's okay.
Yeah, so the null hypothesis would mean that the variables, the dependent and independent variables, are not correlated.
I like
no
that.
relationship.
Just
There's no relationship.
That they are not correlated. I like it because I said that's a clue, right? That is a clue. Yes, I like it. Anybody else? So let me show you something else, then we'll go back. So the null says that the beta naught is 0, right? And then we're coming back here. Anybody else? I'll tell you because of time. Now, when a slope is 0, look at this here. The slope is inclined, or the line is inclined. That's why you can calculate a slope. For a slope to be 0, the line is going to be flat, right? And when there is no, what do you call it? When this is uniformly distributed across the scatter plot, your line is actually flat. There is no upward inclination. There is no downward inclination. If you drew a line, it would just be flat. So Jerry is correct. It's based, the reason why I'm like, I like it is because, yes, I know I led you on with correlation, but it's saying that your line of best fit. Remember, and this is why Jerry is wrong. And again, it's because I led you on by showing you a correlation scatter plot. But remember that what we are talking about here is prediction. And this line is not your correlate, it's not a correlation line, it is your line of best fit. So when we're looking at this thing here, we're saying the line of best fit here is flat. If it starts at 100, it goes from 100 all the way, it is flat. And that is why your beta naught is 0. That is what you're saying. So you are correct in the sense that there is no relationship between y and x. Hence, and therefore, we are unable to predict y based on x. Why? Because...
Sorry.
Yeah.
Just a quick question. You keep saying the beta naught is 0. Do you mean beta naught or beta 1?
Beta 1. I'm sorry.
Okay.
Beta 1. Yes,
Okay.
yes. You're correct. Yeah, because if we go to this line, your beta naught, if we were using this imaginary line at 100, your beta naught is 100. Okay, so correct. Beta 1.
Okay, sorry, please. This beta 1 and beta 0, I think it just took me off the fast lane. Do you want to please help us just reiterate what you say they actually
Okay, let's do it real quick. Okay, so remember this line, this thing. Remember this thing from mathematics. Your y is your y. Your x is still your x. Your m in math, which is your slope, is your beta 1, and your c is your beta naught. That's all that is. So that is why when it says your beta 1, your null hypothesis says, so think about this for a second. Even if you have your C, which is your beta naught, as a good number, for your M, which is your beta 1, to be anything other than 0, it has to be inclined. Because otherwise, if it's straight, and remember the way you calculate your slope is, let's call this point y1 minus y0 divided by x1 by x0, or y, let's call this y prime minus y alpha divided by x prime minus x alpha. If this was flat, just straight on, that means your y prime and your y alpha are going to be the same all the time. And when they are the same, y prime minus y alpha gives you 0, and 0 divided by your x prime minus your x alpha, 0 divided by anything is 0. Does that make sense? Why your null hypothesis says that your beta 1, which is your slope, which is m here, is 0, because there is no way to predict y if your slope is 0. There is no relationship between x and y when your slope is 0. When your slope is inclined, you can say that when x is 0, y is 0. When x is 1, y moves to 1. And when x is 2, y moves to 3. And when x is 4, y moves to 5, and so on and so forth. If your line of best fit is flat, then your slope is 0, and then your x cannot predict your y. Is that okay for a crash course?
Yeah.
Okay. And apologies, because we don't have the time, I may not be able to explain further, but sometimes knowledge, you hear it, maybe don't understand it, you put it in your pocket, you're having a good meal and it just pops in your head, oh, this is what this guy was talking about. So there's a relationship between good meals and knowledge. Okay, that's a good joke, I think so myself. Let's move to example 3. So let's say we're interested in, let's see, what slide are we on? And how much time do we have? I can't tell what slide. We're supposed to go to that slide 34. But let's assume, oh, 23, it says it here. Okay, good. So we have 30 minutes to cover 10 slides. So let's hurry up. Say you're interested in assessing whether there's a relationship between the number of years spent in residency training and the number of hours worked. So basically, they're trying to ask, the more time you spend in residency, does it predict, I should have asked that question, does it predict the number of hours you worked? Okay, so, but that's my interpretation. But look here, right? It's saying here, that wait, I think I'm right. Does the number of years predict the, yeah, we're correct. I thought it was switched. So the linear regression model equation asks, when the independent variable is higher by 1 unit, how much does the response variable increase by? Okay, so let's come back here. So we talked about the null. This is your alternate hypothesis, right? So basically you're saying that there is a relationship between x and y, because your slope is not 0. So because your slope is a gradient, it means that when x moves, y is also going to move. But that does not tell you exactly the magnitude of shift, right? And so when you estimate beta 1, I have to be careful not to keep calling beta 1 beta naught. When you estimate beta 1, you not only want to show that your alternate or your research hypothesis is correct, you want to be able to say to what extent is this relationship. If I've been a resident for 4 years, would each year of residency account for a reduction or maybe even an increase in the number of hours I work per week? And is that number 5? For every year of residency I've worked, my number of hours worked per week increases by 5, such that year 0 or year 1 starting resident versus me who's 4 years, I would have 20, I would be working 20 hours more or less than that person. So you see that coming back here, even though your alternate hypothesis says it's not 0, what you're also trying to do is calculate the extent to which your X predicts your Y. Okay, so that's what you do. Now, we've been talking about principles. This is where the rubber meets the road, as they say. You throw this into your R, you throw this into your SPSS, you throw this into your Stata, you throw this into your Python, you just throw it into something. And this is why you need to know the principles, because, excuse me, if you focus only on the statistical programming, well, in the next 2 years, someone's going to come out, there's R today, someone's going to come out with Y or something, or Python or something, you know, and then you're going to be lost, and you're going to be a numbers cruncher that knows R, but you don't know the principle. So do both of them. Do SPSS, do R, do Python, do what you want to do. Okay, so let's look through this and should we do this? This is technical stuff. This is not exactly principles, but let's go over. So this is what SPS will churn out, right? And it tells you here what your dependent variable is. So your dependent variable is you're trying to predict the number of hours worked, and so it tells you what your predictor is, and it tells you that your predictor is your number of years worked. So let me tell you something real quick. When you're writing a paper, don't write your paper using your variable names. Hours worked is only you who knows that hours worked means the number of hours worked per week or per year or per month. State it out clearly in your papers or in your presentations. Don't say res years was predictor of hours worked. Nobody knows that. You're the only one that knows that. Okay. And you have your R, you have your R square, you have your adjusted R square. We may talk about that if we have the time. You have your F statistic, and you have your, don't worry about your degrees of freedom or your sum of squares. We're not, or even your mean square, blah, blah, blah. We're not going to do that, but we may talk about your R squared, your adjusted R squared, your F statistic, and your value of significance, right? Okay, and let's do that quickly. Does anyone know, and feel free to shout it out, what this R is? The answer is this is your correlational coefficient, and your R square. What's that? What's your R square called? I forgot what it's called, but it's going to be on one of these slides. But your R square is a measure of your variability between your X and your Y. We'll talk about that a little more. Your F statistic is what gives you your p-value. I'm rushing through this, right? So I don't know how useful this is going to be, but your F statistic, remember, if you've done the lectures on t-test, and your normal comparison of means, your ANOVA comparisons, you're going to get an F statistic that is translated into a p-value. And if you remember from last week, we talked about a p-value conventionally. We've agreed that your p-value, when it is less than 0.05, we say that p-value, we would reject the null. But this is greater than 0.05, so we fail to reject the null, meaning we don't have enough evidence to reject the null. We don't accept the null, but we just fail to reject it. Okay, so remember, this is your correlational coefficient. Mathematically, if you give the square of your of, if you give the square of your correlational coefficient, you get your R square. I see it's your what you call it, it's your coefficient of determination. And what it does is it tells you the amount of variability, the extent to which if your X varies, your Y would also vary, right? Okay, let's move to this. Okay, so remember this value here where your hours worked is your dependent variable, and this is your constant. And I'm just going to tell you this. I would have asked it, but your constant would be, suppose when you were, if you're just starting a residency, in this case, if you're just starting residency, so you have 0 number of years as a resident, what is the number of hours you would work? In this case, that is what your beta naught is. Your beta 1, as a refresher, is your multiplier. It is your slope. It is your gradient. It is what tells you that you have a relationship between your X. Remember, this is your X. This is your predictor variable. This is your independent variable, and how it predicts your Y, which is your number of years of hours worked. Okay, so we say, so we're looking at this output here, and we have our beta as 0.97, but look at this constant. So SPSS calls it a constant. Remember when we looked at Y is equal to mx plus c is the constant. This is your beta naught. So basically, you're saying if you have 0 years as a resident, you are going to have work 70 hours, I guess 70 hours a week. That is a lot, if you ask me. But what they're saying here is for every additional year of residency, so when you move from 0 to 1, your number of hours worked per week is going to increase. Is going to increase by 0.97, and if you work 2 years, it's going to be 0.97 times 2. However, when we look at your what you call it, when you look at the significance, it is greater than 0.05. So what do we say? And this can be argued both ways. We say this is the best guess. Some people will say this is actually the real value. This is your estimate. It's just that it is not significant. Maybe it's not significant due to power, blah, blah, blah. But many people would interpret this as saying that this value, and that's what your p-value says, that this value is by chance alone. You got this 0.97 by chance alone. And that's why your p-value is greater than 0.05. Right? Or because it's greater than 0, it's the reverse. Because it's greater than 0.05, you believe that this value occurs by chance alone. And because it occurs by chance alone, you cannot accept it, and you cannot actually use it to make a decision. Whereas some other people would say, well, let's not talk about that. But remember, I was telling you about arguments that people will make. And last week I said we won't talk about it, but let's talk about it real quickly. Last week we said, if you have a drug that reduces people's blood pressure by 20, but it is not statistically significant, a physician can look at this and say, this is a very well done trial. We don't think that this is by chance alone. We think this might be a power issue. But if this is our best guess of what this drug can do, it can reduce by 20, I would use this drug. I don't care about your p-value. I will use this drug and see if it does indeed. But other people will say, no, that 20 reduction is by chance alone. And because it's by chance alone, we are not going to recommend it for you. So these are different arguments. And I remember Ibrahim saying that people are now saying, don't show me a p-value because that would bias me. Show me the estimate and show me the confidence interval, and let me have a discussion about whether I like that. And we're talking about that in terms of clinical versus statistical significance. Okay, so we've talked about you fail to reject the null, whether you reject the null, and let me see, it will be inferred that for every additional year spent in residency, the number of hours worked per week was higher by 0.97 hours, which is very negligible. That's 0.97 hours is 1 hour extra. So per week, maybe over 50 weeks, that's 50 weeks additional per year. So maybe that is an issue. We talked about the p-value. Let's also talk about the confidence interval. Can anyone tell me why we say this includes the null value of 0? The answer is, does anyone want to tell me? Unmute yourselves, quick, if you can get there.
Because the confidence interval is from negative across to the positive side. So because the confidence interval contains a negative value from the lower confidence to the other one. So on the scale within that range, 0 is also part of it.
What scale? That's a good, I was going to say I don't like that, but I like it. What scale are we talking about?
So that's the margin from from minus 0.42 to 2.36. So you move from the negative side of this number scale.
It's a number line, right?
Number line, yeah, up onto 2.3.
Right. So yes, yeah, I like it. But and what we are saying is, suppose it was not just plain numbers. Suppose it was a ratio. What will this null value be? Do you know?
Yeah, it will be 1.
It will be 1, exactly. So don't go away thinking that if it includes 0, it is automatically null or agrees with the null. This is a mean difference, not a ratio. So the difference in hours worked is the difference. If you're a first-year resident, you would work 1 hour per week more than a resident who's just starting, right? So that is a mean difference. It's a difference. If it was a ratio, if you were saying, oh, if you were a 5th-year resident, you work 2 times longer, that null value will be 1. So even though it is not negative, it will start from 0.42 to 2.36, even though it does not go from negative, as Jerry was saying, to positive. In this case, in the ratio, it will be from positive to positive. It will still be insignificant because when it's a mean, your null is 0 because you're subtracting. So 0 means no difference. So when it captures the null of 0 of no difference, you say, no, we cannot agree. But remember the argument we just made. But when it is a ratio of 1 means that the numerator is the same as the denominator. So 5 divided by 5, 10 divided by 10, 1 million divided by 1 million gives you 1. And that 1 becomes your null value. There is no relationship at the null value. Okay, let's move on. Oh God, another poll. I'm kidding. Let's do the poll. Okay, so a trial was conducted to assess whether iron supplement use versus placebo. We've seen this question before. The first answer I see in the chat, I will go for it. I see that Jumoke had mentioned that it was the coefficient of determination. Thank you very much. I like that word, that expression. And I was saying that it is the variability, the prediction of the variability. So I'm going to be quiet for a second, and the first answer to this poll, I will start talking because we have 15 more minutes. A. Someone says the answer is A. Okay, let's go. Let's see. Is the answer A? Wow, the answer is A. The response variable is a continuous variable. So what is the response variable? What is the best reason linear regression is suitable? What is the response variable? Who was the person? Humphrey, tell us. The first person was Humphrey. What is the response variable in this case? Let's hurry.
It is the dependent variable, which is the response variable, and in this case, it is supposed to be anemia.
Anemia. So is anemia a continuous variable?
Sorry,
you're right. I'm just trying to put you.
Yes.
In what case would anemia be a response variable? This is a good question. Remember, when we're talking about, you need to understand implementation, you need to be a subject matter expert. But go ahead.
So I would say likely it can be measured. If it's anemia, can be measured in terms of.
Do you know how it can be measured? And you're correct. Yeah. Anemia is either anemic or you're not anemic. So it is not typically a continuous variable. However, and this is again, sometimes you want to pull this into and say, you know what? Let's make this a numbers thing. Let's give it the properties of numbers. And you would say, instead of using a diagnosis of anemia versus non-anemia, we're going to use the measure that is used to make that diagnosis, which is their hemoglobin levels, which is numerical. Your hemoglobin would go from, I guess, 0. I don't know at what number you die if your hemoglobin went below that level, all the way to about 15 or 14, 12, 13, 14 for men versus women. Above a certain number, it's also a disease. And that goes back to Jeffrey, I think it's Jeffrey's question about what do you do when it's discrete? What do you do? And I told you that it's bound. So even anemia, there is a level. You can't have a hemoglobin of 100 or 2000. It doesn't go on and on. There's a bounded level. So if you do that, when you use those numbers instead of the diagnosis, which is dichotomous, then A is your answer. So do you see that? You need to understand subject matter. My recommendation, don't go and research a thing you are not knowledgeable about. Okay, note, there are extensions of linear regressions where the response variable does not have to be continuous. That's beyond the scope of this class. I'm not a statistician, and so maybe it's even beyond my scope. I don't know. Okay, oh God, now we're talking about the R squared. So we're talking about the coefficient of determination. And what I think we want to note here is that it is a measure of the goodness of fit of the linear model, right? Now, look at these two and follow me here, right? These two lines are not parallel to one another. These two lines are not parallel to one another. They're not the same line. One of them looks steeper than the other. And you might have to use your eye of faith or whatever to see that they're different, right? So consider that in an alternate universe, there are two lines of fit for the same data. You know, there are two lines of fit for the same data. You are going to say, what is the best line of fit, right? What is the goodness of fit? And this, you don't even need an alternate universe. You can see that when you add a different predictor to your model and you want to compare, you know, there's something called parsimony of your models. You want to say, should I use model A that has 7 variables, or should I just use model B that has 4 variables? And sometimes you want to use this R squared to determine what is the better fit for that line that you have drawn through your data. And that is where your R squared is useful. Now, your R squared is also So the mathematical formula is the explained variation over the total variation. Let me spend 1 or 2 minutes explaining that. So earlier, I was saying that your coefficient of determination tells you the extent to which when X varies, Y would vary, right? So Y varies, and okay, Y varies because what we mean by Y varies, let's say we are talking about the length of babies, right? So the length of babies would vary from baby to baby. The length of babies would also vary depending on how old they are. In 2 cases, these babies are varying. The lengths are varying, not the babies. The babies are also varying. The lengths are varying. But what we are trying to understand is the extent to which, when you vary the ages of these babies, their lengths vary. Let me come back to what I just said. The baby's lengths are varying from baby to baby. That's one variation. The baby's lengths are varying because there's a measurement error from the nurses or the doctors or whoever is measuring their lengths. But the baby's lengths are also varying based on whether they are 1 day old, 1 week old, and so on and so forth. That is the total variation, all the variability that you can see in Y, in the length. But you want to understand the extent to which X, which is the age, forget about the measurement error, forget about the difference between babies and the genetics between the babies. You just want to know, what does X, how does variability in X, which is your age, predict your Y? And so that is why you now have the explained variation of X on Y divided by all the variation you're seeing from different reasons. That is your what you call it? That is your R square, your coefficient of determination. Now, how do you interpret this? So look at this value, it's 0.01. Now, the way that people would tend to interpret it is they would change this to a percentage, and this is 1%. So basically, they're saying that the variation in the number of hours you work per week, only 1% of that variation in hours worked per week is caused by your years of residency. Why is this important? When you're doing your regressions, what you're going to find out is that even when your p-values are significant, right? And of course, you have your adjusted R square. This is a simple linear regression. We'll talk about adjusted R square maybe when we talk about multiple, but just stay with me for your R square. Even when you see significance in your regressions, you might find that your R square and your adjusted R square are actually quite low. So you may say that smoking, and this is a bad example because we've established that it is cause. Smoking is a predictor or is a cause of cancer, but is the R square, how high is the R square? Do you think it's 20%? Do you think it's 30%? Or do you think it's low? Go and look at every regression you've done and look at your R square and tell me. So you see that there is, I don't know if you've read this article about the web of causation. Someone wrote it, that it's true that an X may predict a Y, but the extent of variability is caused by so many things that X alone may not be. It may be the single most important. It may be the best. It may be the thing that you can control for. But your R, go check it. You'll find that your R square is many times very, very low. Okay, two challenges with the R square. It increases when you add more variables, and this is why you have to do an adjusted. But we have only one variable. That's why I'm talking about your R square. You have to, and it cannot determine whether your estimates are biased or not. Okay, so your R square is telling you that this is the extent of variability, but it cannot tell you whether your answer, whether what you found in your research is actually correct or not. Your p-values cannot exactly tell you whether they're correct or not. Does anyone know why? Because there's a chance of type 1 error. But let's skip this. We have 6 more minutes. So this is just to show you the adjusted R. Okay, no, I think since that is I think what you want to understand here, let's see, what I just wanted to show us here is look at this R square. This adjusted R square is not just small, but it's negative. And if you remember your mathematics, you know, you cannot have a square of a number that is negative, right? So what I'm trying to explain, what I'm trying to say to you at the end of this class is what I started to say to you at the beginning of the class, which is, or not maybe at the middle of the class, which is sometimes numbers behave like numbers. They're not necessarily the truth, right? How would you explain this adjusted R square? Well, my answer is you don't explain it. You don't explain it. Is your result significant? Yes, maybe you go with this as significant. No, this p-value is not significant, as you can see. And maybe if it was significant, maybe your R square would change. But note here that your typical, just because you put data into your program does not mean that you have arrived at truth. You must understand the principles, you must understand how they fit, and that's how to be a good researcher as opposed to be a numbers cruncher. Okay, so that is wrap up. We have 4 minutes. Feel free, feel free to tell me if you have questions, and I will also stay for 10 minutes past the hour to take questions. And I believe we can stop. Recording this session. Thank you. All right, Yusuf.
Thank you so much.